Okay, so hello and welcome to this TA session for the course of Physics of Materials, which is an NPTEL course for the year of 2025, starting from August session. And my name is Mohammad Tahsin. I'm the TA for this course, and we are in week 6 now. So let's start our session, and let me start by joining from my iPad so that you can see my screen. Okay, so let's start by sorry, let me adjust my volume. Yeah, it should be better now. So let me start by giving you a brief recap of the things that we discussed last time. That's in week 5. Okay. So last week we looked at an alternative to the need for having an alternative to Maxwell-Boltzmann statistics, and the need was because as per the Maxwell-Boltzmann statistics, if we follow them, we come up with models for electronic conductivity and thermal conductivity. We come up with values which either overpredict or underpredict some of the quantities as compared to the experimentally measured values. So that forces us or compels us to look for an alternative method or an alternative treatment so that we can correlate the experimental findings and the theoretical understanding of the material. So so that's why we need an alternative framework in which we can come up with statistics of corresponding to that framework, which can basically explain these properties which evidently the Sommerfeld the Drude model, which is based on Maxwell-Boltzmann statistics, that is not able to capture some of the quantities. That's not able to predict some of the quantities correctly. So to address that, we will eventually develop a model which is called the Drude-Sommerfeld model, which will be the topic of today's session. But that Drude-Sommerfeld model, it's based on Fermi-Dirac distributions as opposed to Maxwell-Boltzmann distributions. And the Fermi-Dirac distributions, they come from incorporating the quantum mechanical principles into building the statistics. Okay, so we have to incorporate the principles of quantum mechanics to come up with this Drude-Sommerfeld model. So that's the overview. We had some discussion related to why we need to apply these quantum mechanical principles so as to come up with a better model. And so there is a basic assumption that we make in Maxwell-Boltzmann statistics, which is that all the particles in Maxwell-Boltzmann statistics, they are classical particles. They behave as classical particles, which is not true for electrons or other subatomic particles as well. So in Maxwell-Boltzmann statistics, we assume that the particles are identical and distinguishable, right? So this is the assumption that is not applicable when we go to subatomic particles. So we will see that these particles actually, they are identical and indistinguishable from each other, right? So why does this affect why does this matter for subatomic particles? It's because, so roughly if we take a look at the length scales corresponding to atomic or subatomic species, we see that the atoms are of this order of 10 to the minus 10, which is the angstrom level, and protons and neutrons, which live inside the nucleus, so to say, these have roughly the size of 10 to the minus 15 meters, which is also called a Fermi level, right? And if we look at the electrons, there are estimates that the size of electrons is somewhere around 10 to the minus 18 meter. Right? So it's because of these size effects that the quantum mechanical principles become more evident and prominent in these species. So for classical particles, Maxwell-Boltzmann statistics will predict the parameters correctly, but since the electronic contribution to specific heat and the electronic conductivity, these properties come because of electrons. So the species, concerned species here are electrons, and the size of electrons is very small, as we can see. So it's because of these properties or such length scales that the quantum mechanical principles become indispensable, and we have to account for those principles in order to predict the overall behavior of the ensemble of electrons. So we took one example to distinguish between the classical particles and the quantum mechanical particles. So here, if we let me use a pointer. So if we look at the first case here, we see that we have two balls which we call B1 and B2, and if we assume that this is the classical picture, okay, classical picture, these are treated as classical balls, let's say two tennis balls, and if we set them on these trajectories which are represented by arrows and we let them collide, now after the collision, if we assume that they get reflected across this collision point, and the ball 1, which is incident like this, it gets reflected as shown, okay, and similarly the ball 2 comes in, it hits the other ball, and this transfer of momentum gets changed, and this is reflected across this. So this is the final position of the this ball B2. So in this case, we can easily distinguish between balls B1 and B2 throughout their trajectory. Okay, so throughout the entire trajectory of this motion, we are able to clearly demarcate which one is particle 1, which one is ball 1, and which one is ball 2. Right, and this is true of classical particles. But if we have non-classical particles or quantum particles such as electrons, okay, which are represented by E1 and E2, so if they if we set them on these trajectories so as to make them collide with each other, then in this collision process there is actually a chance that these two got interchanged, okay, and that interchange is such that we cannot say with certainty that this particle here would retain its position, would retain the same trajectory as was the case with classical particles, or will it follow a different trajectory. Okay, so this is true of, let me say, quantum particles. Okay. So that's the difference, actually, what we need to account for in our models, and the statistics which will be built upon treating the electrons as indistinguishable particles, that is what is going to make the difference between the outcomes of Drude model and Drude-Sommerfeld model. So now there are certain questions. For example, we could ask, why is there a probability that these two got interchanged and we never knew about it? Okay, or why are the particles indistinguishable? So these are very deep questions, as the physicists would say, that there are different levels at which we can understand them, And the easiest level which I prefer, or which I understand, is that this is a consequence of the uncertainty principle, right? So if we are able to keep track of the momentum, then we lose. There's an uncertainty in assigning a position to the particle. Okay. So ultimately, whatever quantum mechanical behaviors there are, somewhere these are all a consequence of the uncertainty principle. And in certain references, it is written that some physicists even believe that the uncertainty principle is like an axiom for physics or for quantum physics, and all the other behaviors that emerge from these quantum mechanical systems, they are just consequences of this axiom. Okay. So we briefly had a look at the history of quantum mechanics, and it all starts in the beginning of the 20th century. And these are the main problems in physics that were unsolved problems at that time. And people believed that the reason that existing theories at that time could not explain these behaviors, for example, the black body radiation or photoelectric effect. So the physicists believed that it could be a matter of some correcting factor or small modification of the equation that is needed to explain these effects. But no one even knew that it could the solution to these equations, or the solution to these problems, could basically open up door for an entire new era of physics. So if we look at we took a look at a couple of these problems. The first of which is the black body radiation. So black body radiation is simply the radiation which is absorbed or reflected by or radiated rather, not reflected, by a black body. Now what's a black body? A black body we define as a body which can absorb and emit radiation at all wavelengths. So no matter which what's the frequency or wavelength of the radiation that is incident on it, it absorbs that throughout the entire spectrum, as long as the temperature of this black body is below the temperature of the surroundings. And similarly, if we raise the temperature of this black body to be above that of the surroundings, in that case this black body starts to emit radiation, right? Because it tries to get into thermal equilibrium with its surroundings. So can you mute your mic, please? Thank you. So if we raise the temperature of a black body to above that of its surroundings, in that case the black body starts to emit radiation at all wavelengths. Right? This is in accordance with the first law of thermodynamics. No, that's conservation of energy. Yeah, so this is a consequence of second law of thermodynamics, right? Which gives a direction to the heat transfer process. So what happens if we now measure the spectrum that comes out of this black body? Okay, so this is the concept of a black body which was put forward by Kirchhoff. So here, if we look at this spherical shell, now I am only able to show a section of it here, but it's actually spherical and it has a pore here. And through this pore, through this cavity, the radiation enters or leaves the system, right? And there is some kind of a dissipator, rather I should say a reflector, some kind of a reflector here in the form of a cone, which reflects the incident radiation so that it gets reflected across. Multiple reflections happen and it finally gets absorbed. The radiation gets absorbed inside the body. And similarly, if a radiation is emitted from anywhere here, this conical bump here, it makes sure that it gets reflected across the body so that it can finally leave from the body. Okay. So if we measure this experimentally, this is the kind of trend we see in this black body radiation, that if we take a graph of spectral radiance and wavelength, and spectral radiance is nothing but its power per unit area per unit wavelength. Okay, if we can see the definition here, intensity is power per unit area, and then spectral radiance is intensity per unit wavelength. So this plot here, it's actually power per unit area per unit wavelength. So if we look at the plot, we see this kind of a trend, which is shown by the line in the red, right? And this is actually the what's called the black body radiation phenomena. Okay? And if we use this Maxwell-Boltzmann statistics to understand this phenomena, what we see is this dotted line in pink color, right? This is what is predicted by the Maxwell-Boltzmann statistics, and this law which predicts this distribution is called the Rayleigh-Jeans law, which is based on Maxwell-Boltzmann statistics. So we see that when at low energies, so low energies correspond to high wavelength, low energies correspond to high wavelength or lesser values of frequency, right? So at low frequency, we see that the trend predicted by the Maxwell-Boltzmann statistics, it's in line with what's observed experimentally. But as soon as the wavelength is decreased, we get into the region of high frequency, high energy. So we see that this leads to this curve as predicted by this Rayleigh-Jeans law. It violates the experimental findings, right? It deviates from this a lot, and this is called the ultraviolet catastrophe. Now so this basically laid the stone for quantum mechanics, and Max Planck, and there was a mistake in this spelling which Lalita pointed out last time. So it is P-L-A-N-C-K, Max Planck. So basically Max Planck observed, he assumed that the energy, if we have intensity present at some wavelength, right? For example, let's arbitrarily choose this wavelength, and we look at the intensity corresponding to this wavelength, right? So if this is non-zero, if there is some intensity present at that frequency or that wavelength, it means that an oscillator inside the body, an oscillator is vibrating, which is emitting the frequency at that radiation. And what Max Planck assumed was that the energy released by that oscillator is directly or needed to excite that oscillator. So these are equivalent statements, right? If an oscillator is activated by a certain amount of energy, when it's activated, it will oscillate at the same frequency to emit the same energy or same frequency of radiation, right? So what Max Planck assumed was that energy needed to activate this oscillator, that is directly proportional to the frequency, okay, frequency of the radiation. And then he, just to treat this as an equation, he introduced a constant h, which came to be known as Planck's constant. And once he redid all the calculations, okay, he followed the same footsteps as followed by Rayleigh-Jeans, but with this particular assumption, he came up with a modified expression for equating this E of lambda t, which is now the spectral radiance, with the wavelength lambda, right? And what he found that when he plotted his equation and tried to fit the experimental data with the curve that he obtained, because this h was an undetermined parameter at that time, when he tried to fit his curve to the experimental curve, he found out this value of h to be this 6.55 into 10 to the minus 34, which is the current accepted value is this. So this is how the Planck's constant came into being, and the entire field of quantum mechanics started, right? And following this, the photoelectric effect, which was known experimentally, observed experimentally even before Max Planck's work, but it was again unexplained, okay? And Einstein followed in the footsteps of Max Planck to basically explain this photoelectric behavior, and he also used the same principles So basically he assumed that if there's an, so what is the photoelectric effect? Photoelectric effect says that there's a incoming radiation and it gets reflected off a polished surface, and if we increase the frequency of this radiation at a certain radiations, the electrons will be emitted from the polished surface. Okay, and the kinetic energy of these ejected electrons is directly proportional to the frequency of this radiation. So to explain these effects, Einstein used this quantum mechanical picture, and he borrowed this H nu, the description of the description of energy used by Max Planck, and he was able to come up with this photoelectric equation that won him a Nobel Prize later. And the velocity of electrons, the ejected electrons, calculated using this equation, that was very close to the experimentally determined values as well. And so, but the point is that in Max Planck's in his theory to explain the black body behavior, what he assumed inherently was that matter consisted of small oscillators, right? Or that black body itself, that consisted of small oscillators which get activated at a particular frequency and then start emitting, right? But what Einstein did was he assumed that radiation itself consisted of small packets of energy which have a certain frequency and certain energy associated with them, right? So this is like, philosophically speaking, it's quite different assumptions. In one assumption, we assume that the matter consists of some kind of quantized oscillators, and in the other, we assume that the radiation consists of certain kind of oscillators. Now, at this point, radiations were thought of to be waves. It was confirmed because radiations showed diffraction, they showed interference, and it was established that radiations behave as waves, right? So, but what Einstein assumed was it consists of small particles which are called photons, right? So although Newton had earlier, maybe a couple of centuries earlier, Newton had hypothesized that the light radiation, it consists of small particles called corpuscles, and the theory was called corpuscular theory of light. But since there was no mathematics involved from Newton's side to explain this theory did not gain much acceptance up till this point. So now Louis de Broglie was another scientist who basically saw these assumptions, and he came up with his equation, which is very famous, and it's called de Broglie's equation, in which he assumed that any particle, be it or any matter in general or any radiation, has both characteristics. It behaves as a particle, which is to say that it has certain momentum, and as well as it behaves like a wave. Okay, so it has certain wavelength as well. And he related these two quantities, like lambda characterizes the wave behavior and p characterizes the momentum, characterizes the particle behavior. He related them by the Planck's constant h. Okay, and so what it says is that if we have large particles which have large mass and therefore large momentum, their particle behavior will dominate, and as compared to their wave behavior. And for matter which has low mass, right, for example electrons, protons and all that, their masses are of the order of 10 to 10 power minus 31 kgs. So for such particles, their wave behavior will dominate. Okay, so so using this theory, okay, so this was one more like a milestone result. And finally, one of the problems that was unsolved in the beginning of 20th century was the atomic spectra of atoms, and it was known experimentally that atomic spectra is discrete, right? It is not emitted. So if this is the kind of spectra that we obtained from experiments, right, the spectra did not come out to be continuous across all the allowed wavelengths, but only at certain wavelengths we could see the intensity in the spectrum. And again, Niels Bohr used this uh, concept of quantization, and he basically applied it to the electrons moving inside or revolving around the nucleus. Now he further hypothesized that the angular momentum of electron is quantized, right? It's discrete, and by making that assumption, he was able to correctly predict this discrete spectrum of atoms, as well as he gave his model of the atom, which is very widely accepted till date, right? So using this quantization, he could figure out what are the energy levels, why the energy levels are discrete, what are their exact values, and what are the radii, like corresponding to different orbits, right? So basically, as you move away from the nucleus, the energy also increases, right? And this is the ground state energy. For hydrogen atom, which has only one electron, these are the so this corresponds to the atomic radius, and this corresponds to the energy needed to basically make this hydrogen atom into a hydrogen ion, right? This is the energy of that electron. So this pretty much summarizes. There is one important and probably the last one, which is the Schrodinger's equation, right? So basically, when it was accepted, when de Broglie's hypothesis that all matter has a wave behavior and a particle behavior, when this was accepted by the community, then the question that came up was, okay, if something is a wave, or something displays a wave-like behavior, then it should satisfy a wave equation. Okay, and the question was, where is the wave equation? What is the equation that this wavelength satisfies, right? That this wave satisfies, because we are talking about a wave now, and there's a wavelength. But where is the wave equation? Usually, if we deal with elastic waves or electromagnetic waves, we have a wave equation. From that, we derive what's the wavelength corresponding to that wave. But here we have an inverse approach. We have a wavelength, but we don't have an equation, and we basically don't know where it came from. So this is why Schrodinger's he wrote down an equation by making an analogy with the so this is basically the wave equation for a string. We can easily so this is the form of the equation is similar to that of an electromagnetic wave. So this has two orders of differentiation with respect to time, and two orders of differentiation with respect to space, right? And it's a linear partial differential equation. So by making comparisons with this equation, Schrodinger came up with his equation, and which is shown here in this box. This is the Schrodinger's equation, and the variable here, it's not displacement, or it's not electric field or magnetic field, it's psi, which is called the wave function. And so this V here, it represents the potential in which that particle or that body or that matter is kept. Okay? And psi basically, so the hypothesis is, if we know psi, that is the Schrodinger's hypothesis. If we know psi, we know everything about the system. So basically, the equation needs to be solved for psi. And then, okay, so then it was asked that what does the psi represent physically? And so there's something called as Bond's interpretation. Of psi, right? And what he said was, if we take the modulus of the psi function, because it's a complex function, right? Psi will have a real part and an imaginary part. So if we take this quantity, right, which is equal to nothing but, because psi is a complex function, we can talk of its conjugate, right? So whatever is the imaginary part, just negate that, and that will be the conjugate of this wave function. And if we then multiply it with psi, okay, and this will give us, so this is what this quantity is, and he said this defines the probability density. Probability density of that particle, right? So if we assume that we are there's some one-dimensional domain which goes off to infinity in one direction, minus infinity in one direction, and there is some origin where we start. What he said was that if we take this mod psi square and we integrate it between minus infinity to infinity, it should be equal to 1. And this is called the normalization, and physically it means that the particle has to be somewhere in this domain from minus infinity to infinity. Okay, and in realistic, more realistic situations, this psi square, it could look at something like this. Okay, it needs not to be defined for every value between minus infinity to infinity. It could be something like, let's say this, right? It's 0 everywhere and somewhere it peaks up. So that's the, if it peaks here, for example, we see such behavior in one particle kept in a one-dimensional box in some certain length, and outside of that length, if okay, let me draw to make it a little bit more clear. So if this is a one-dimensional domain, and there is some length, let me say this is minus L to L, so the length of the domain is 2L, and this is the origin, and let me suppose that the potential here is infinite. Let me draw it like this. Many of you would have seen this already in your undergrad physics courses. So if we say that the potential here is infinity and here it's infinity, so that the particle cannot escape this this region, right? So if we look at the probability, the psi square, mod psi square, it is 0 here, and mod psi square is 0 here. Okay, and inside this box, this particle can be present in a, so depending on energy, what the energy of this particle is, the wave function could be something like this, or if we, so this is the basic, if it has the lowest energy, the ground state energy, right? So let me call it EG, energy ground, or E naught, right? That's the convention. Then if this particle increases its energy, psi looks like this, something like this, and similarly so on, right? We can find the wave shapes for different for different energies. Okay, and now so this is basically the reference. Now this is psi, right? Psi plotted as a function of x, but if we take psi square, then it becomes positive, right? There is this negative loop turns into positive. So let me draw psi square in some other color. This is psi square, right, for this energy level, and for this energy level it would be something like this. Something like this, yes. So this value will get doubled because it's square now, right? And the negatives will turn into positives. And these locations where the psi square peaks out, this is the most probable location where we can find the particle, right? So this was Max Born's interpretation of this psi, the wave function psi. And finally, there is one last thing. Probably it's having the first thing, which is Heisenberg's uncertainty principle. Again, maybe all of you know this already. Would anyone like to tell me what's the Heisenberg's uncertainty principle? if anyone wants to add something on this principle from what you know. Yes,
The
Lalita.
product of the del x into del p vector then equal to h cross by 2.
Very right. So del x and del p is greater or less?
Greater.
Greater or equal to h cross by 2, right? And what is del x?
So that is uncertainty position and del p uncertainty momentum.
Okay. So what does this statement say? Like, what is the statement of Heisenberg's uncertainty principle?
So we can calculate the position and moment, exact position and momentum simultaneously. So we can only calculate their uncertainty position.
Right, right. That is right. So what do we mean when we say that we cannot calculate their position or momentum simultaneously? What do we mean by calculate? Do you understand my question?
Yeah.
See, when we say we can't calculate their position and momentum at the same time, is this calculation, does it refer to some kind of measurement, some kind of experimental device that tries to locate their position and momentum?
Sorry.
So let me try to. So yeah, this is correct what Lalita said, that this is the uncertainty in position. Okay, you all know this already. I'll just clarify one point. This is uncertainty in position, and this is uncertainty in momentum. Right? And if we take the product of these uncertainties, it has to be greater or equal to some constant, okay, which depends on the Planck's constant. Now when we say, okay, so the statement says what Lalita said is that the position and momentum of the particle, this applies to basically any particle, cannot be, let me bring this all here, cannot be calculated at the same time. And this is usually the source of confusion, where most people where this uncertainty principle seems to confuse most of the people, is that what do we mean by this calculation, and what is this calculation about? Is it some experiment, we are running an experiment and we cannot predict the values correctly, or what does it imply, right? So one thing that we need to take care of and that we need to remember always is that this statement or this principle has nothing to do with experiments. Okay, that's the first point. It has nothing to do with any kind of experiment, any kind of measurement, or anything like that. Okay, so then what does it say? What does this delta x mean? Okay, it means that this momentum and position, so I'll just replace this word. Okay, so the correct word here is defined. Okay, at the same time then we need to complete it a little bit more, right? The position and momentum of the particle cannot be defined at the same time up to infinite precision or arbitrary precision, right? So what does this mean? It means that we cannot so for these it is basically non-intuitive, right? We cannot understand it in a way that we are most familiar with, I mean, in terms of real life examples. Because if we take the real life examples, suppose there's a car which is moving at some velocity, constant velocity, okay, and now we know the mass of the car, we know the velocity, so we know its momentum, right? And we can, at any point, if its velocity is v, and let's say that at time equal to 0 its position is x equal to 0, at that time its momentum is 0, and as it starts to move, at any time t, its position will be given by vt, where v is the velocity, right? And its momentum will be given by mv. So we know its position and momentum for its entire duration, right? And there is no uncertainty there, right? But that is because we are treating this object as a classical particle, right? But in fact, what the principles of quantum mechanics say, and what the computations show us, this can actually be derived, right? We can derive this principle, and what it says is that the definition itself, we cannot define the position of a particle to infinite precision, right? There will always be an uncertainty, and what this uncertainty results in is this probability distribution, right? That's why we talk about probability distributions in quantum mechanics, right? Everything is related to probability. We can never know for exact, we can never define what the exact position means, right? Because it has to always uphold this law. This principle has to be always upheld. So it's because of this uncertainty, or because of this, so the point here is it's the lack of definition, not the lack of measurement, right? It's not because we are limited by powerful enough instruments which can give us a very high resolution position or momentum of the particle. It's a fundamental property of matter that it obeys this uncertainty principle, and we cannot even define what it means for an electron to have, let's say, a particular position. Okay, we can always talk about in terms of probability, because there is always an uncertainty involved, and the same holds for momentum as well. Right? So final thing is Pauli's exclusion principle. Now, would anyone like to contribute here? You already know some version of Pauli's exclusion principle. What does this principle say? Any ideas?
Is that
Yes, Lalita.
in this principle states that to formula there is no for all quantum numbers, then
Right, correct. That's absolutely correct. So, two fermions cannot have the same set of all four quantum numbers. Right? And Now, so here's my question. So fermions, these are just particles which have half integer spin. Okay. So now whenever we say fermions, you can simply think of electrons. Okay. These have half integer spin. Okay. What that means is the spin, if we calculate their spin along any axis, it will be plus minus 3 by 2 h cross and so on. Okay, this is what the value of spin is going to be. Now, so where does this affect, or how does this affect the Maxwell-Boltzmann distribution that we saw earlier? Can anyone answer that question? In the Maxwell distribution, so let me put the question clearly. In the Maxwell-Boltzmann statistics that we derived in the earlier class, how does this concept of Pauli's exclusion principle affect that distribution? Any ideas? Okay, so this is actually what we are going to discuss today. Okay, how do these quantum mechanics principle, and today we will be so the derivation that we are going to do, that will only include in particular, that will have this Pauli's exclusion principle somewhere inbuilt in that derivation, and we will not go to the absolute level of depth. We will not for example talk about the quantum mechanical picture of an atom and then develop from that. Instead, what we are going to do is we are going to just do statistics in a wholesome manner. Okay, what's the outer picture, and the goal here for today's derivation that we are going to do, it is to basically argue in a qualitative way how does the Boltzmann statistics differ from the statistics that we are going to do today. Okay, it's called the Fermi-Dirac statistics. How do the properties change because of these two statistics, and what is the difference between these two approaches? Okay, that causes the properties to change. So we'll do that today. So before that, I just want to quickly, okay, so let me just write here. Okay, now this is an important concept that we are discussing, how to integrate quantum mechanics into let's say these models, Drude model. So I just spent some extra time here, and I want to start off with some simple these MCQs. We'll do some of them, and then we'll shift to the topic of today. Okay. Okay, so let me just write one simple MCQ, and you will try to guess what's the correct answer here. Okay. So the Maxwell-Boltzmann statistics indicates that as temperature increases, okay, then we have options. Option A, higher energy states are increasingly unoccupied. Option B, so option B is higher energy states are increasingly occupied. Okay. Option C, lower energy states are increasingly occupied, and option D is that lower energy states are increasingly occupied. So what should be the correct answer here? I can give you a minute to read it. You can attempt the answer. You can say the answer whenever you are ready, or if anyone has any comments or suggestions on this question. Anyone?
Option B.
Option B. Yes, that is indeed correct. Yeah. So only one option is correct, or there is some other option also which is correct?
If option B is correct, then option C will be correct.
Yes. So that's exactly what's happening here. Both of these options are correct, right? And we can see this from if we just recall what the distribution was. Okay, the Maxwell-Boltzmann distribution. We had energy on this axis, and here we had number of states, right? And the distribution looked something like this. So for some temperature, this is the temperature T1, and let me use another color for temperature T2. This is the temperature T2, okay, and here we have T2 is greater than T1. So this is the kind of distribution that we saw, right? And if we see here, at higher energy levels, as we increase the temperature, right, more states are being filled here, and at the low energy, at higher temperatures, lesser number of states are being filled as compared to T1. So this is actually what gives us the value of thermal conductivity, right? In root model, right? This knowledge how the temperature or how much energy do we need to put in to basically change the energy states here and here, right? That corresponds to this temperature, and that's how we obtain the value of thermal conductivity. But in this case, if we relate it to this question, we see that both options B and C are true. At higher energy levels, more states are occupied. At lower energy levels, as we increase the temperature, lower energy states are increasingly occupied, right? Unoccupied, not occupied. Okay. So let's take a look at another question. Planck's equation reduces to Rayleigh-Jeans equation, and the options are: at high frequencies, B, at all frequencies, C, at high wavelengths, and option D, it's at room temperature. Okay, so these are the four options. So which one of these is true? Anyone? So we looked at one distribution today, right? Which was something like this. We had wavelength here, and here we had spectral radiance. And the experimental results show us a graph of something like this, right? But the Rayleigh-Jeans law, what it predicts is a distribution of something like this, right? So this is what Rayleigh-Jeans law predicts, right? And this is the region of ultraviolet catastrophe, right? So in accordance with this graph, the correct option should be option C, right? So because we saw that yeah, I think I missed one thing here, that Planck's equation, right? If we okay, let me write the equation. It is actually the explanation of this is here. Right? So this is the expression. Let me copy this. Sorry. And paste it here. Right. So this is the Rayleigh-Jeans law, this one. And I did Rayleigh-Jeans. And when Planck took into account, this is Planck's equation, right? He took into account the quantum mechanical behavior of matter, and then if you substitute that in this equation, if you substitute that lambda is large, this lambda is large, so basically if lambda is large, then you have what happens if lambda is large? Maybe there's some error in this equation because so this expression, yeah, so if we expand this factor, okay, this exponential into its series, right? So we can expand this using the Taylor series. We can write a series expansion of this, because we know that e to the x is equal to 1 plus x square by 2 factorial and so on. And when we write that expression, so let me just do that actually. It's a good exercise to do. So we can write that e power hc over lambda kt, where k is the Boltzmann constant. It can be expanded as 1 plus, so now treat this whole as x, right? And then we know the expansion of e power x, this is equal to 1 plus x plus x square, so it's the same thing squared, by 2 factorial, right, into 1 by 2 factorial, plus so on, right? And now if we ignore, so if lambda is large, then lambda square is much greater than 1, and then lambda square is even larger, right? And we can ignore the values from, so this term onwards, if we ignore them, neglect them, because they will be very small as lambda is in the denominator, then we can only keep these two terms, right? And now if we look at what's the value of, I can shift this 1 to LHS to get the value of this denominator. So in that case, this spectral radiance, so I'm just substituting this equation here in this equation. What we get is, it will be equal to 8 pi ch over lambda to the 5th times, so now it's 1 over this, right? So I will write the reciprocal of this equation, which is hkt lambda kt over hc, right? And if we evaluate that, it will be equal to 8 pi k t over lambda to the 4, right? And if we look at, this is the exact same law as predicted by Rayleigh-Jeans. Right? So in the large wavelength limit, this Planck's law, it reduces to the Rayleigh-Jeans law. So that's why this will be the correct option here. Right? The Planck's law reduces to Rayleigh-Jeans equation at high wavelengths. So let's do one more conceptual problem. Okay, this one. So this question is about the photoelectric effect, and the options are: the photoelectric effect can be explained using the wave nature of light, right? Option B, it can be explained using the particle nature of light. Option C, can be explained using the particle nature of electrons. And D, can be explained using the wave nature of electrons. So which is the correct option here?
Option B.
Option B. Yes. Sorry. Was there any other comment? Does everyone agree that it's option B? Does anyone have an objection? Yes, Lalita.
So it's wave nature of light.
Wave nature of light, yeah. So option B, right? What about option C?
So option B is particle nature of light.
Yes. So
then
that, yeah. So the option B, that is correct, right? So what about option C? Is that right or wrong?
yes, sir, right. The particle nature of electron also.
Yes, yes. So actually we use both of these assumptions in the photoelectric effect, right? We use the particle nature of electrons as well, right? We use this assumption as well. But there's one important we should be careful, because at this point, if we go historically, right? So if this question is asked today, maybe it makes sense to consider both of these options as correct, right? But historically, if we go in chronological order, this photoelectric effect was explained somewhere around 1905, right? 1905, 1906. But the first time it was concluded, or it was demonstrated, that electrons can behave as waves. The first experiment was which one? Which experiment gave us this information that electrons can behave as waves? Does anyone know? Okay, so it was Davison and Germer experiment. Right? And if I am correct, this was in 1920s. This experiment was done in 1927. Right? And this was the first demonstration. This came after de Broglie's hypothesis that matter can be a wave as well as a particle, right? And basically what they did was they saw diffraction pattern created by electrons, and before that it was known that diffraction is a property of waves. Only waves can diffract, right? So they associated this wave-like nature to electrons as well. So this is the first time that we concluded, or that we had seen, that electrons could behave as waves as well. And before this 1927, everyone, like, there was no question about this. Electrons were considered as particles. These were not considered as waves. But today we know that electrons can behave as waves as well as particles, right? And so if this question is being asked today, then the correct answer is we consider both of these options to be true. But in 1905, when Einstein did it, he did not know that electrons were waves, right? He treated them as particles. So yeah, that is the thing we need to be careful about. Okay. So okay, let's start with something that is the main purpose of today, which is Drude-Sommerfeld model. So what is this Drude-Sommerfeld model? We are familiar with Drude model now. We have discussed that over. We have been discussing that in great length. But what is the Drude-Sommerfeld model, right? So let me just write a few characteristics of this model. Okay. So like the Drude model, it's also a free electron model. Number second, so it applies quantum mechanical principles to the Drude model. Okay, that is the correction that it imposes. Okay, Drude model is entirely based on classical approach, that is the this Maxwell-Boltzmann statistics, but Drude-Sommerfeld model is based on quantum mechanical principles. Okay, and number third, it uses, or it applies, what we call Pauli's exclusion principle. Pauli's exclusion principle, right? And okay, I'll make a small comment on this later. Okay, what's the next one? Assumes that the potential is constant within the metal? What does this mean, that potential is constant within the metal? What it means is that there is no preference that an electron would like to be in one position or another position, right? If there is a square, let's say our metallic sample, it's a square of length 1 centimeter, right? So, and there's some free electron present inside that sample. Then this, if the potential is constant, that means there is no preferred location that this electron would like to stay at, right? Since the potential is same, it would be it can easily delocalize. It can be anywhere, right? There is nothing that forces it to be at one particular position, or that prefers one location to other. Okay, that's the meaning of this assumption, and this is the assumption that we will make while deriving the model. Okay, and this is equivalent to saying that it's a free electron model. Okay, so the first assumption and the fourth assumption, they are not very different from each other. If it's a free electron model, that means it's free to be anywhere. The electron is free to move inside the sample without any hindrance. And the same is, so the assumption 4 is actually a technical specification, or something. So it's a setup that ensures that 1 is followed. Okay, assumption 1 is followed. So next thing that we are going to impose is electrons are identical and indistinguishable. This is another difference from the Maxwell-Boltzmann distribution, right, where we assume that they are identical and distinguishable, but here they are identical and indistinguishable. And this assumption is same as saying this, right? The second assumption, it applies quantum mechanical principles to root model. Okay, so since we are assuming we are applying the quantum mechanical principles, so all the electrons will be treated as indistinguishable. So this follows from second assumption. Okay, and similarly, the last one is behavior is governed by Fermi-Dirac statistics. Right. So here the difference is that the classical root model that used, or that was based on Maxwell-Boltzmann statistics. Okay. So these are some of the characteristics, features, or assumptions that we make in this Joule-Sommerfeld model. Okay. So so now the first thing that we should see is, how does this affect the distribution? Okay, how do these assumptions or these axioms or these suppositions, how do they affect the distribution of electrons, right? Which is different from Maxwell-Boltzmann statistics. So as before, so we will keep the setup mostly the same. Okay, we will say that there are energy levels. So this is the setup now. These are energy levels, and I will call them E0, E1, E2, and so on up to ER. Okay, and now I'm going to assume something which was not there in the Maxwell-Boltzmann statistics, which is, let me call them number of states. Okay, for each energy level we are defining the number of states. Okay, so these number of states, let me call them S0, S1, S2 up to Sn. So what does this number of states mean? is this number of states means there's a, so it basically shows vacancy. Okay, and an energy level of E naught, which has energy E naught, can at most accommodate S naught number of fermions, okay, or S naught number of particles, right? Similarly, an energy level of E1, it can at most accommodate S1 number of particles, not more than that. So this is the difference between the earlier statistics, classical distribution, and this distribution, right? So for example, if we had 100 particles in classical distribution and we were looking at the lowest energy state of the system, we could take those 100 particles and place them in the lowest energy level. That would give us the lowest energy of the system, right? But when we come to this principle, okay, this quantum mechanics principles, we see that corresponding to each energy level there is a number, right, which puts a limit on the number of particles that you can put inside that energy level. Okay, and this is a consequence of, so let me write as a note that this is a consequence of Pauli's exclusion principle. Try with capital P. Pauli's exclusion principle. Okay. Now we could argue that there should be only two levels pertaining to each energy level. There should be only two states, right? Because somewhere we know that the Pauli's exclusion principle says that there cannot be more than two electrons presented at one energy level, right? And the spin has to be different, which is to say that all four quantum numbers cannot be same. They have to be one has to be plus half spin, one has to be minus half spin, right? But right now we are not generalizing to any kind of system. We are writing it for general fermions, okay, not necessarily electrons, right? We just want to see this how this statistics behaves, right, in a wholesome manner. So all that we are going to comment for now is that there is a limit on the maximum number of particles that can be put there, and I'm not going into a greater detail here what that limit actually corresponds to, because that will depend on the type of fermion that we are dealing with. For electrons it will be 2, for some other fermions or for some hypothetical particles it could be anything, right? But there will be a limit. That is what Pauli's exclusion principle tells us, right? Pauli's exclusion principle is not just applicable to electrons, it's applicable to all systems, right? So right now we are just going to assume that there is a limit, there's a maximum limit that corresponding to each another energy level that we are denoting by S, okay? And similarly for rth energy level there will be SR number of states, okay? And third thing that we are going to assume is that distribution, okay? Distribution. Now how is the distribution going to look like? Distribution, let me put a line here. So the distribution corresponds to actual number of electrons, okay? Let's say that this is N0, N1, N2, so on up to Nr. These are the actual number of particles present inside these states, okay? So now what are the constraints on the system? Okay, what are the constraints on the system? Okay, so constraints, okay? Constraints. Now the first constraint that we assume is that total energy is fixed. Total energy of the system is fixed. Okay, and this means that is the system is in a the system is in thermal equilibrium with its surroundings. Okay, that's the first constraint we apply on our system. Okay, so what's the second constraint? Right, so what are we finally just so let me say that first. Why are we doing this? What's our quantity of interest, right? We want to figure out what is the distribution. Okay, what's the most probable distribution? So in the most probable state, which will give us the what we call the this equilibrium state of the system. Okay, in that equilibrium state, which is the most probable state, what is this distribution like? How is this n0, n1, n2 related to the energy and the states, okay, and the number of states? So we want to develop a functional relationship between these quantities. Okay, that is our objective here, and we are doing it under a certain set of constraints. The first of which is that the total energy is fixed. Okay, and what is the second thing? Second constraint on the system: number of particles are also fixed. Okay, we are not allowing particles to leave the system or more particles to enter the system. Number of particles in the system, that's also fixed. Right? So these are the constraints we are working. Now, so first thing that we denote is, yeah. So let me first write. Okay, ultimate goal. So the ultimate goal is to find a distribution. Actually, it should be find the distribution which corresponds to the most probable state. Most probable state. Okay, and we will call that distribution, let that distribution be n naught, and I am going to place a bar over it. Okay, so this bar represents that it's a vector quantity. Okay, and why is it a vector quantity? Because n naught will be something like this. Okay, it will be n0 bar, n1 bar, and so on up to nr bar. Okay, this is what this quantity will be. Okay, at the most probable state, what is the number of particles that are present inside each energy level? Okay, that is what the information contained in n naught. So my goal is to eventually find this distribution and relate it to the how is this n naught bar related to the energy E naught. Okay, and similarly for other states as well, other energy levels. So I'm going to call it n naught, and now so I'm going to define a quantity. Okay, I'm going to define a quantity which is called f of E, and let me call it f of EI. Okay, and f of EI is going to be the probability that a state probability of occupancy, okay, occupancy of states inside the energy level EI. Okay, so inside this energy level EI there are now SI number of states, okay, and depending on how many of these states are filled, we can define a probability function, probability distribution function f of EI, and if we evaluate this function at the particular value EI, it gives us the probability of occupancy of states for that energy level, right? So this is just a, simply said, it's a probability distribution function, and what it will be equal to, if you guys know about the conditional probability, okay, it will be f of EI given n, let me call it n bar, okay, EI given n bar times probability of n bar, okay. So what is this quantity? So this quantity gives us the same thing, okay, probability of occupancy, probability, so probably I should add here, this one on the left hand side is the total probability of occupancy of states inside the energy level SI, and this quantity does not care about what the distribution is, okay. This quantity here, it does not care about what the distribution is, okay. It just wants to know that we give it an energy level, we give it a particular energy level, and we want it to return us the probability of occupancy. But in turn, what will actually happen is it will depend on distribution, okay. This probability that we want to calculate, it will depend on what kind of distribution is present there. That will determine the probability of occupancy. So that's why on the right hand side we write it in this form, and this expression f of EI given n bar, it is the probability of occupancy of states inside the energy level EI, provided that the distribution is n bar. Okay, so this is the difference between the terms on the left and right, okay. And then what is P of n? P of n bar, P of n bar, it's the P of n bar is, yeah, so it's the total number of ways, it's a probability, right? Probability of, so it's the probability corresponding to that state n bar, okay. What's the probability among all the distributions that the system can have? What is the probability that the distribution is n bar, okay. So it's the total number of ways of constructing the distribution n bar divided by total number of ways, and you can also call it a microstate, right? Okay, divided by total number of ways of constructing all possible distributions. All possible distributions. Okay, so what we essentially have used here, if some of you may be familiar with this is nothing but this is Bayes rule. Okay, Bayes rule on conditional probability, and this is called actually conditional probability. Okay, why conditional? Because we are asking this, so we are trying to find the probability of this EI, probability of occupancy of states in EI, provided that something is given, right? This condition is given. So in this case, the condition given is that the distribution is n bar, and then we multiply it with the probability. What is the probability for that distribution to occur, right? So if we sum this quantity, it will give us if we sum this quantity, it will give us the total distribution here. Okay, so there is actually on left hand side there should be a summation. Here it should be a summation over all n bar. Okay, we have to do this for all states. That is what will give us the total probability of occupancy of states for this energy level. Okay, so now what happens is so first thing, if we look at this term here, okay, in the denominator here, this total number of ways, it's going to be constant, right, given the information, because in our system E0 is constant, S0 is constant, similarly E1, E2, E3, all of these energy levels are constant. They are not changing with the way we change the distribution. And similarly, the number of allowable states, S0, S1, S2, they are also constant, right? So the total number of ways in which we can construct all possible distributions for a given energy, now that is also constant, right? But these n bar, it will depend on what exactly a particular distribution is. Okay, so this quantity also, it will not affect anything qualitatively, right, because it's a constant, right? So there is some notation. This quantity is represented by omega n bar, okay, and this quantity is omega total. This is just some notation. Okay, so omega n bar is the number of ways in which n bar can be constructed, and omega total is total number of ways of constructing all the possible microstates. And then if we use this in our equation above, what we get is f of EI is equal to f of EI given n bar times P of n bar. Okay, or if we just rewrite this, it will be omega n bar divided by omega total. And again I missed the summation. This is going to be a summation. Okay, so now consider the most probable state. Okay, consider the most probable state. Okay, most probable state. Now if we consider the most probable state, what that means is, and let the distribution be n naught as we assumed. So we have already assumed for the most probable case the distribution is n naught bar, right? And if we put that into the equation, we find that now at what is the most probable distribution? At most probable distribution, this omega n naught bar divided by omega total, this value will be very close to 1, right? This is something that we saw in the classical model as well, and we were doing Maxwell-Boltzmann statistics. What we said is that as the number of particles in the system increase, then the most probable state, number of let's say the number of microstates corresponding to this most probable state, they supersede all other microstates combined. Okay, so this is a consequence of that reasoning. We are using the same reasoning here, right? The most probable state will be it will have more probability of occurrence than all other states combined. Okay, that's why its probability will be very close to 1, and we are going to use it actually here. So what we are going to write here is f of ei, and if this is n, and if this quantity is a constant now, if we substitute it to be n, and so let's see what we get. Okay, so here we are summing over n bar, and now we are assuming that n bar is equal to n naught, then we will have simply this, that the probability of occupancy of states in energy level ei, it is equal to f of ei given n0. Right? So this is going to be the probability of occupancy of the state ei. Okay. So simply said, what this equation tells us is that the probability of occupancy of a particular state is the same as the probability of occupancy of that state at the most probable state, right? Most probable macro state, right? So that's what it gives us. Now let's see what's the number of ways of arranging a particle, right? Number of ways. So this equation as such, we have not inferred anything from it. All we have said is that in a way that the only distribution that is going to matter is the most probable distribution, the distribution at the most probable state, and at that state it's going to govern what is the probability of occupancy of a certain state. That's all we have said for now. But now we will go to compute the number of ways. Okay, compute the number of ways in which a microstate can be constructed. We still don't know what this n naught bar is. Okay, so what are the number of ways in which a particular microstate can be constructed? Okay, and this we represent by omega and I. Okay, and this will be equal to Si divided by, it will be actually Si factorial divided by Ni factorial into Si minus Ni whole factorial. Right? And if you are sharp enough to observe, this is the formula for what? Anyone wants to say? Does anyone recognize this formula? You will have seen this formula somewhere in maths, in probability.
Combination.
Yes, exactly. So this is the number of combinations, right? So NCR is equal to n factorial divided by r factorial into n minus r factorial. So similarly, this will be SI C Ni, right? And what it means is number of ways of arranging Ni number of particles in, number of ways of arranging SI number, so SI number of states by filling Ni number of states at a time. That's what this means, because NCR means what? Number of ways of arranging n particles by taking r at a time. Now this number of states in our case, this is SI, so this will correspond to the total number of states available at a particular energy level, and we are filling it, those number of states, available states, by taking ni number of particles, right? And why we are taking combination? Does anyone recall? Can anyone recall what was the equivalent thing that for Maxwell-Boltzmann statistics? When we wrote the same omega ni there, we assumed something else instead of this, right? So if you go back and check, there we assumed NPR distribution, right? These are the number of permutations. So if you take a look at that expression, right? So there was this factor was missing there, right? You will not find this factor there. Okay, that is because, so this is where we are integrating the fact that quantum mechanical particles are indistinguishable. Because if they are indistinguishable, then, so what is the difference between a combination and a permutation? So if we have 5 particles, let's say 1, 2, 3, 4, 5 particles, and if they are identical in every way, then that's a single combination, that is one combination, right? But that same combination I can permute in 5 factorial ways, right? So if I consider that there is a difference between these particles 1, 2, 3, 4 and 5, I give them some kind of label. If I am able to distinguish them, then I can arrange them in 5 factorial ways. That is the number of permutations corresponding to that system, right? But if in all of those permutation, 5 factorial permutation, those are all a single combination, right? And we can even check this, right? Because, okay, let me not digress because I have very little time. So this is where we are, this is the step where we are integrating the fact that the particles, quantum mechanical particles, are indistinguishable. Okay, so rest is just mathematics. Okay, it's just to come up with this this fact that we have to use combinations here and not the permutations. So now, okay, so this is for one energy level, right? The energy level which has SI number of states and Ni number of particles, right? But we have to fill every single state, correct? So we have to fill every state. Okay, let me write this way. If this is E0 and S0, E1, S1, E2, S2, and so on. Okay, so I have to do this job, I have to fill it with N0 number of states, N1 number of states, N2 number of states. I have to do all of these jobs one after the other, right? So this is an AND job. So there are two kinds of jobs in probability. One is AND job, one is OR job. So the OR job is if I have to do either this or this or this. Okay, but if I have to perform all of these jobs one after the other, then I take the product of probabilities. Okay, so in AND job, the total probability is the product of individual probabilities, and in OR job, the total probability is the sum of all probabilities. Okay, so in this case, since we have to do every job, we have to fill each state, we will take a product of all the probabilities, individual probabilities. So what we get is omega n bar is equal to this omega n1 times omega n2, right, and so on up to omega nr, right? And the condensed way of writing it as is this product, this capital pi, it means product. So I have to carry a product over I of omega and I. Okay, this will give me the this omega n, the probability, all the number of ways in which I can form this microstate n bar. Okay, So now the constraints on the system are that summation of EI and I is constant, right? As we discussed, the total energy of the system is constant. Okay, at each energy level, if there are Ni number of particles and the energy is EI, then the total energy is summation of EI and I. And the other thing, we assume Ni is constant. Total number of particles are constant. So if we sum the number of particles at each energy state, that will give us the total number of particles. Okay. So then what is, if we substitute all of this, what we get is, okay, what we get is omega of n bar is equal to product over I Si factorial divided by Ni factorial into Si minus Ni factorial, right? And we have to minimize this. So since we have to find n naught, right? We have to find an expression for n naught. This n naught will happen when this n naught will be achieved. At that time, this omega n will be maximized. Okay, so this factor, this omega ni, number of ways in which we can attain a particular microstate, that will be maximized for n naught bar, right? Because this is the most probable distribution. So what we have to do is we have to maximize this expression. So this is the expression that I have to maximize while respecting these two constants. Okay, and this type of problem is called a constrained optimization problem, where this is the objective function, okay, and these are the constraints. Okay, and such problems are solved by Lagrange method, or like the method of Lagrange multipliers. Okay, now I don't have time to go into the detail. So basically you differentiate with respect to each coordinate of this n bar vector. You differentiate with respect to each coordinate and set that equal to 0. Now if you do all that, what you get as a result is that f of EI, so there will be some constants which have to be evaluated and all that. So if you do all that process, what you get is f of EI is equal to 1 plus e to the power EI minus EF divided by KT. Okay, so this is now the probability of occupancy of the energy state EI. Okay, and it is related to temperature, so it depends on temperature. Okay, the probability distribution function will depend on temperature, and it will also depend on the energy level, the particular energy that we are talking about. Okay, now if we plot this, we get a distribution of this kind. Okay, so here I will plot f of EI, right, on this axis, and here I will plot energy, simply EI, the energy of each state, right? That's what I'm plotting on the x-axis. And if I plot this function, this is what the plot looks like. Okay, and I should mention that, let me make it a little bold. Okay, let me draw the figure, then I will explain. Okay, so this is 0 Kelvin. Okay, it's not okay, it is 0 Kelvin. Now if we raise the temperature, you'll find that the distribution looks like this. Okay, and then it looks like maybe this. Okay, so this is enough. Right, so in black it is T1, 0 Kelvin. Okay, and in green is, or let me call it, in black I have T naught equal to 0 Kelvin. Again it's looking like okay. Then in the blue I have T1, which is greater than T naught, and then at red, in red I have T2, which is greater than T1. Okay, so what I am doing here is I am plotting this function here because it depends on temperature. I am plotting it for different values of temperature. Okay, and what is this EF here, because it was not in our observations before. This EF is called the Fermi energy. Okay, so basically Fermi energy is the energy if you keep filling the particles energy levels. Okay, so now we have this kind of situation. This is E naught and this is E1, and similarly up to, this can go on up to infinity, right? But let's say this is EF. Okay, so this EF is, it corresponds to the ground state. Okay, so when we have ground state means the state of lowest energy. Suppose I have n particles in my system and I am filling those n particles here. Now because of the Pauli's exclusion principle, I cannot fill on all the n particles here, right? Because there is a particular number of, there's a limit to the number of particles which I can put here. So if I put S naught number of particles here, then I am forced to go to higher energy level to fill in the rest. And when that is filled, I am forced to go to the higher energy level, right? So similarly in this way, if I fill all the energy states up to full, the last energy level which will be filled because of these n particles, right, where the nth particle will go, that level is called the Fermi level, right? So this is the Fermi level, and at 0 degree we will have the ground state, right? So what this graph is saying is that till the energy level EF, so this value is 1. Okay, so what this graph is saying, that at the ground state till the energy value EF, okay, so all these energies, this will be 0, this will be ground state, E naught, E1, E2, E3 and EF, right? All the states lesser than EF, including EF, have a probability of occupancy equal to 1, right? That means all of these states are filled, and there is no need for a system to have higher energy than EF because we are at ground state, right? We would like to have the minimum possible state. So the probability falls to 0 after EF, right? We don't have to go to higher states. But as we increase the temperature in this equation, as we go to T1 and T2, we see that the distribution changes like this. Okay, there are some states which cross this EF level, okay, the Fermi energy level, right? They cross this barrier and they go to even higher states. That is what causes the temperature of the system to rise. Okay, and the more you increase the temperature, you will see that the states will go to higher and higher energy levels, right? Because the red is here the highest energy level, you see that the highest energy levels are occupied, okay, as compared to green and black. So this and one more final point I would like to make about it is that we see that in this Fermi-Dirac distributions, only the energy states which are near this Fermi energy level, only they contribute to, or only these levels interact with temperature. because this region is same for every temperature, right? Even at temperature T1 and T2, these probabilities are not altered, right? Only the energy states which are near to this Fermi energy, only they interact with temperature. And this is actually the biggest difference between the Fermi-Dirac distributions and the Maxwell-Boltzmann distribution. Because if you plot a similar plot for Maxwell-Boltzmann distribution, sorry, we are going over time, but I will just conclude with this final point. So if we draw a similar diagram, so let me call it P of EI there, and let me call it energy states for Maxwell-Boltzmann. So what we observe there is that distribution changes like this. Okay, so first at 0 Kelvin, oh sorry, we are plotting probability, right? The probability for all energy states, right? So this is energy states. So the probability will be 1 for all energy states at 0 Kelvin, right? But as we decrease the temperature, increase the temperature, what will happen is, sorry, these are energy states, so probability will be 1 so it should be like this, right? It should be like this, right? Because we are at ground energy, so all particles will have ground energy state. They will be in the ground energy state, right? And as we increase temperature, let's say this blue and green temperature, the distribution changes like this. Okay, so again this is T2 greater than T1, and this is T1 greater than T1 greater than T0, which is equal to 0 Kelvin. Okay, so what we see here is that all the electrons, right? All the electrons interact with the temperature. The temperature causes all of these electrons to raise in their energy levels, right? It takes every electron to maybe next level, or it causes a redistribution in all energy levels. While as in Fermi-Dirac distributions, only the energy levels near the Fermi energy, only those interact with temperature. Okay, so this is the biggest difference between these two models. And this distribution, which is based on this Dirac distributions, Fermi-Dirac distribution, this is called the Drude-Sommerfeld model. Okay, so this is just to explain the qualitative behavior between these two models. What we are going to do next time is we are going to actually come up with the model, so come up with a number of, so what we have not done here is, here even in this graph we do not know, or from this equation we do not know what is the number of particles in each energy level, right? What's finally called the density of states. We do not know that number here, we only know the probability, right? So in order to evaluate a particular quantity, let's say thermal conductivity, we need to know what's the exact number of particles in each state. So that's what we are going to do next week. And yeah, so I'd like to stop here. If there are any questions, you may ask. Any questions?
Can you please go to the page where you have written SI-CNI combination part?
Yes, here.
So here you have written the number of ways of arranging SI of states by filling NI number of states.
Yeah, so yes, it is a little confusing, sorry for that. So what I meant to say here is that, see, generally when we write NCR, that means number of ways of arranging n particles if we select r particles at a time, right? But in this case the analogy will change, right? Because now this n, which is the total number of objects you have, now here I am considering the total number of states that you have at that energy level, So I have to somehow, okay, let me draw one. So let me draw it here. So let's say I have 5 energy states, okay, 5 energy states at energy level EI, and let's say this is state 1, and similarly state 2, state 3, state 4, and state 5, okay, and I have, let's say, only 2 particles. So this is particle 1, this is particle 2. I have 2 particles, right? Now what are the combination? Let me call it P1 and let me call it P2, okay. Now I don't want to call it S1. Oh yeah, we can call them S1 actually. That's what we represented. S1, S2, S3, S4, S5, right? So if we make the combinations, what are the combinations going to look like? P1 S1, this may be 1, and P2 S2, right? So this may be one way. The second way would be, let's say, P1 S3 and or P1 S1 and P2 S3, and similarly we can populate all the number of ways in which we can arrange this, right? So but what is important is that P1 S1 P2 S2, it is same as P1 S2 P2 S1, okay. This combination is unique, okay. So the point that I'm trying to make is, what we are doing here is we are filling these energy states by taking the particles. So let me see what I have written and see, yeah, here. So number of ways of arranging SI states by filling ni number of states at a time, right? Because I am filling only ni is 2 in my case, okay. At a time I am filling ni number of states, and the total states I have to arrange is SI. So those 2 particles can go anywhere. It is just that once they occupy those 2 positions, then if I flip them, that is the same combination again. That's the only difference. Is it a little clear now?
Yes, sir.
Okay. So this is about this ni. I am arranging ni. I am filling ni number of states at a time. Okay. So this is the thing that we need to concentrate on, and I have to arrange all of them, all states, by filling ni number of states. Okay. So thank you. That was a good point. Yeah. Any other questions? Okay, so we can stop here, and I'll meet you all next week. Thank you.